Hello again, my dear students, and welcome back to the Informatics 2 class. And today we're going to start a new topic called linked lists. We're going to be talking about this topic in this lesson, number 16, and in the coming few lessons as well. In this presentation, we're going to talk about the properties and limitations of array representation. So far, all topics we have talked about assumed the array structure representation. So at the very beginning, we're going to talk about this structure and see what are its properties, advantages, and disadvantages. And then we're going to look at alternate representations of these data structures. And we're going to concentrate and focus in our presentation on the linked lists as an alternate representation for data structures. And then we're talked about linked lists. We will declare these linked lists, see how we define them, and then how we're going to use them after that. Okay, let's start from the first thing. Properties and limitations of array representation. Well, the very basic idea about array representation is that it is contiguous space in the memory. So given that my array is defined as this, in the memory, the way this structure is actually implemented is where we have a contiguous locations in the memory comprising this array. So if this array, let's say, is called A, then I will reserve in the memory contiguous locations of whatever type, whatever data type this array is going to hold, consecutive locations in the memory with a size equals to the maximum number of entries that are going to be inserted inside this array. So the main idea is that this space is contiguous. That's one after the other. Well, what kind of problem I could have in here? Well, in many cases, I could face the problem of not finding enough contiguous space in the memory to allocate for this array. And this could occur especially when the array size is really big. The memory is actually used by all functions and all applications running inside the memory. Here's a memory map. This is the system memory, okay? And the system memory is shared between so many applications. So maybe application 1 is using this space, and application 2 is using this space, and so forth. And here and there, I could have some empty locations which are not assigned to anybody. So this is empty, and it's available for use by any other application. Now, assume that I started running this application, which is going to reserve as part of its memory requirement a location for some structure called array, okay? And I need something like 2 kilo memory to hold that data for the memory. However, this empty space in here is not actually enough for that. Well, what can I do? All the memory is being used. I could have an empty space in here. But again, this space, which is empty again, but it's not 2K as well. So I could have little bits and pieces here and there. If I combine them all together, they will give me the 2K requirement, but none of them is actually by itself a 2K contiguous block of memory. And in that case, I'm going to have a problem in implementing my structure. And that means I won't be able to run my program accordingly. However, the best advantage about using arrays is that once I know that the space is really contiguous, then I know the location of the next element when I know the location of the current element. Because simply, as we all remember, the array is stored in memory in rows. So that's the first row, then comes the second row, third row, and so forth. So if this is element number I, let's say, I know for sure where is the position of the next entry. It's simply at I plus 1, and if let's say the size of this was 1 byte, assuming we're talking about a character array, then the location of the next entry is located at whatever I plus 1. If I'm talking about integers to where I have the one location containing, let's say, 4 bytes, then the next entry is going to be located at whatever position I have in here plus 4, and so forth. So always I can find the location of the next entry from the current position of the current entry by just incrementing the size of the elements inside the array structure. So I can go anywhere within the array by decrementing my index back and forth within this contiguous bus comprising the array. And that's a very simple way of looking at the array, and this is the main advantage basically of the array. However, as I said, the major limitation of the array is that I have to have enough space, contiguous space in the memory to allocate it. Otherwise, I won't be able to allocate the space for the array. And now, to delete and insert any elements to the array, that's very straightforward. You can go to the required location, okay, and you can overwrite whatever data you want in there, and that way you're deleting the previous data and you're inserting new data. You don't have to physically remove the data when you delete, okay? You just ignore it. You just consider that I don't have valid data in there. And at any given time, you can add in new data by going to the proper location within this contiguous set of locations, and insert your new data the way you like. So insertions and deletions are very simple and straightforward because we know the addresses, we know the indices, how to go backward and forward in the array structure. However, array has a fixed bound on the minimum and maximum. That means when I reserve in the memory this block of data, this block of spaces for my array, then these are my bounds, as a matter of fact. This is the first entry in my array, and this is the last entry in my array. Okay, I can't go before this location because it's out of my scope and my array pointer cannot reach that. And I cannot go beyond this because this is basically not mine and it could be used by some other application. So if for any reason your array was of size, let's say array of 10, let's say, then the indices in here you're going to have are from 0 to 9. Now, in the middle of your program, if you attempt to say something like array of 11 or of 10 or whatever after that, then you're going to a space outside the scope of your array. And there are no guarantees what kind of data you have in there, and there are no guarantees that you're not destroying actually the data located in these locations. So you cannot go always beyond the scope of your array. You always play within this field, within your bounds. Okay, some compilers, as a matter of fact, would give you an error even if you attempt something like this, because they will tell you right away that you're going outside the bounds of your array. So you are bounded by the first and last entries in your structure, and that's all within this contiguous space that you have allocated for the memory. So that means the maximum size of array has to be declared when the program is written. And we do a declaration statement like this. Like I would say something like integer array A of 10. That means, and that's done at the very beginning of your program, and that means please allocate in the memory a block of data of type integer, 10 consecutive locations for me. Okay, and once you do that, this structure is actually fixed, and you cannot change it during the execution phase of your program. Okay, and what does that mean? Is that a problem? Well, in a sense, there's no problem as long as you know what you're doing, and as long as your entries will not exceed this number, as a matter of fact. However, it cannot be changed during the execution time, as I said. Once you start running your program, this location or this block of data is going to be reserved for you in the memory, and you can read write to it the way you like. However, you cannot change the size of that block anymore. Okay, if you realize in the middle of your program that you need more space, then you have to stop your program and go back, edit the code, and change the size in here. And that's the basic limitation of defining the structure in this way. So problems, if you have too many elements, I already reserved space for 10 elements, and I realized that, no, I need something like 20. Oh, it's too late. This is a problem. And if you attempt to write to the memory more than just 10 entries, you're going to have an overflow. On the other hand, let's say you reserved in the memory a block of 10 consecutive locations for your array, but then you realize during the execution that you're not using no more than 3 to 4 elements. Then why to waste this memory space? We're wasting too much space, and in this case, we're talking about poor utilization of the resources that we have, and mainly the memory resource. So having a fixed static structure like this could have the problem of overflow. That's when you realize that you have too many elements to insert in your structure in the middle of execution, or when you don't have that many actually, and you're not utilizing the whole space you're reserving, and in that case, you're not utilizing very well the memory resource you have in your computer. Well, what's the alternative? The alternative is to look for something that's more dynamic, more flexible, to allow me actually to change the size along the road while I'm executing my program. Well, generally, let's look at this model here, and it's a very interesting model. Our applications actually come up here, which says application program. It's the highest layer in the structure of our software. Actually, this program is not going to talk directly to the memory, but rather I'm going to have a layer down here with basic functions, basic operations that are going to be performed on the actual memory. So I could have a module, a low-level module, to search for something using whatever binary search or sequential search, to delete entries, to traverse structures in the memory, to create a new structure, to destroy an existing structure, something like that. These are basic operations, and we call them ADT class codes. And ADT stands for abstract data types. So I will have down here abstract data types. The user program talks and accesses these abstract data types. These abstract data types now work on the actual memory. And basically, we would like these basic ADTs to be of type dynamic, so that they allocate memory on demand and they free memory on demand as well. So that way, these abstract data types will be more efficiently using the memory, the actual memory that we have. So that's basically the model each programmer is using in real life and in real practice. So instead of talking in your application directly to the memory, you will be talking to these modules here, and these modules in turn talk to the memory and talk to other resources you have on your system. So basically, as an application program, the only thing you need to know is the concept of the data type you're using. And you're going to be talking to this data type in a sort of standard interface. So you know what's inside there as a whole, or you take it as a black box. It's transparent to you. You don't care about the basic details of that data structure. The only thing you care about is the idea and how to use it, not what's inside it. Okay, and that's what we care about. So later on, somebody else could come to this middle layer and change the definitions in there. Well, he can change with whatever new technology that we have on our computer. But for you as a program, you don't have to change your programs each time there is a change down there. As long as the changes in here keep the standard interface between this layer and the user programs, then your program doesn't have to be changed after that, even if the hidden data structure has changed. Okay, and that way this makes the development much more efficient and much more actually productive. So we can work with the objects of this type by using a set of predefined operations. These set of predefined operations actually is what we call the standard interface between these data types and the application or user program. We do not really care, and we don't necessarily know what's exactly inside these objects down there and how they are implemented. They could be implemented using arrays, they could be implemented using other data structures, as long as I know how to talk to them, how to call them whenever I need to retrieve data, how to call them whenever I need to write data, how to whatever operation I need to perform. There is a standard interface between these objects and my user program. Then I don't really physically have to know how exactly these abstracts or these data types have been defined. Okay? So if we absorb this and if we digest the idea of having this three-layer model, then we can proceed and define our data structures after that. So the implementation can be changed. Not even a bit in the application program will be changed, as I said. I can change in the middle layer here, which has the actual implementations. Here's my application program, okay? And here's the actual resources that I have on my computer. And one of these resources, of course, is the memory. So as long as the interface in here is a standard, okay, then I don't care how this implementation has been carried out on these resources, because I don't actually get to this point, but rather I'm talking to these applications or to these classes or to these objects from this side. So keep the interface here the same and change the implementation here the way you like, and you're going to be safe and you don't have to change your program at all. So different implementations then are possible, could be used in different cases. All right? Your program is going to stay the same, different implementations here, but the interface is standard and you are safe. Well, some of these structures that we already covered and talked about are the stacks and queues. So stacks and the queues are basically of these abstract data types. However, these are not the only way of implementing actually the structures that we're talking about. We could actually implement these structures using matrices, a matrix or an array, and that's what we did. Or we could use what's so-called linked lists, or what's so-called trees or binary trees. Or better yet, another structure called network, where I have many connections. These are different ways of implementing actually physically structures in the memory. And in this course, we're actually going to concentrate and focus on the linked lists. So in this class and in the coming few classes, we're going to talk about the concept of linked lists and how do we really utilize memory using this linked list, and we're going to see how it's different from this classical structure of the array. Linked lists. Basically, a linked list is a sequence of elements called nodes. So each entry is called a node, according to the definition in here. And the list as a whole, or the linked list as a whole, is a sequence of these elements or of these nodes. Space allocation is much more flexible. How is that? Well, basically, the space is not contiguous this time. How is that? Here's my list. Bunch of nodes like these. Okay? And these nodes actually are going to contain my data, the entries. However, it's not like the actual array where I have actually a series or a sequence of entries or nodes. But in that case, when I had the array thing, these nodes were consecutive actually in the memory. However, in the case of the linked list, actually these entries or these nodes are not necessarily contiguous in the memory. So I could have the first one here, here's the memory, and this is my first node of the list. Okay? So I'm just going to call it list. The second node does not necessarily go here, but rather could be down here. So this is node number 1. This could be node number 2. And node number 3, I don't know, maybe somewhere here. 4, 5, anywhere in the memory basically. So I could go back and forth in the memory wherever there is available space enough to allocate for one entry in the list, then I will just allocate it. It doesn't have to be contiguous. So that way, the location of the next element is not simply the next in line, but rather it's somewhere else. So it's not implied the same way it was in the case of arrays. In case of arrays, because the elements were, or the nodes were contiguous, then I know for sure if I'm at node I, then node I plus 1 comes right after that. Well, in the linked list, that's not the case. Of course, I have to know where it is then to be able to access all nodes in the list. And then I have to find some sort of a mechanism through which I can go from one node to another. So the story here is a little bit harder than the case of the array. Okay, it's not as simple and straightforward as that, but we're going to find a simple way of doing that. Let's see how we're going to do that. Each node points to its successor. Well, that's excellent. How to do that? Well, this is the first node, as I said in here. Basically, I'm going to reserve always at the very end of the structure defining this node, a pointer which is going to point to where the second node is located. Okay? So it points to its successor. And then this one at the very end of it, I'm going to have a pointer which is going to point to the third one. So it's like a chain, as a matter of fact, okay? To where you have a piece of string or rope to where you're going to tie your pieces together. So this is the first piece, okay? And you have your first rope in here, and that's where your hand is actually holding to, okay? And then I will have another piece of rope here that's going to tie the second node, and then to the third node, and so forth. Okay? And I have to make sure always that these pieces are tied together very well, otherwise I'm going to lose them. Because if I lose the rope in here, or the string in here for any reason, then this node and all subsequent nodes are going to be lost. I can never tell where they are located in the memory. This node only knows about the location of this one through this rope, piece of rope that we have in here. Okay? In computer terms, at the very end of this node, I'm going to have the address of this node. Okay? And this will have the address of the next, and so forth. So there is no chance, no way for me, for this node to know what is the address of this node. Okay? Directly. To go to this node, I have to go through this node, and then this node will lead me to the next node, and so forth. So each point or each node in the list points to the next node in the list. Of course, needless to say that there is nothing before the first. There is only your hand holding the whole list. So the only thing that I need to know to access all entries in the list is this one, because this is pointing to the first one, and then the first points to the second point to third, and so forth till I get to the very last node in the list. So this is the most important and crucial actually pointer that I have. Keep it tight in your hand, never lose it. Okay? So that's actually what we generally call the head or the top of the list. So the first entry, there's only a pointer that points to its head. And this is what we're talking about in here. And this defines the rest of the list, actually, or at least gives you the map to where the list of the nodes are located in the memory. And of course, at the very end, this is my last node. I don't have any other nodes in there. So basically, when I do this, this is going to be pointing to nothing. We're going to use this symbol, the earth symbol, to indicate that it's pointing to nothing. Well, in C, nothing means null. So basically, each node is going to be pointing to the next node. I have head in here pointing to the head of the list, to the first entry in the list. And the very last node always points to null. And that indicates the end of the list. So basically, nothing after last node. And that means it points, the last node points to null. The idea of a linked list. For every node in the list, there is a pointer in the node definition that points to the location of the next node in the list. Here's a picture, a better picture than this one. This pointer is what's called head, and it points to the beginning, to the first node in the list. And then in the definition of the structure of each node, I have here a pointer that points to a node. So basically, the pointer here is of the same type as this pointer. That means it points to a structure of this type, which is called node or list node. Okay? So again, so this one points to the next. And at the end of this next one, I have a pointer that points to next, and so forth to the last one, and the last one points to null. And we're using graphically this symbol to indicate null. Okay, linked list components. The major components that we need to worry about and be careful about when we talk about this. Basically, here's my list, consecutive nodes, and here's the last node. I have the very first one is what's so called linked list head, or for short, head. So this is the first component, and this gives me enough information, okay, so that I can access all nodes in the list once I know this. It's very important and perhaps the most important component in the linked list. And then after that, this basically means a linked list node. So this is a node, as well as this one, and this one. Okay? In each of these nodes, I have, in its definition, a pointer that points to another node of the same size, of the same structure, same definition, and same in here. And for this one. And the very last one, actually, as I said, points to null. This one, that points to null, to nothing. So basically, there are three main components that completely identify the structure of the linked list. Basically, head, the first pointer that points to the first node in the list, the nodes themselves, and the fact that each one of them actually have a pointer that points to a structure of the same type, and the very last node always points to null and to indicate the end of the list. How many nodes do I have in a list? Well, that depends. And that's why we're going to be always using dynamic dynamic memory allocation to allocate space for nodes of the linked list. And the list could have just one node, 2 nodes, 10 nodes, 100. It depends. I only gonna allocate memory for a new node whenever there is a demand for a new node. Otherwise, I will just live with whatever I have. 3, I'm happy with 3, that's okay. And you make the last one pointing to null. In the middle of the operation, you realize that you need one more entry. Okay, so that's when I'm gonna allocate memory for the new node and add it to the list. Okay, and so the size actually of the list could change during the execution of the program. I could add more nodes to my list, or I could delete nodes from the list. That way I'm freeing space and I'm only using the space that I need in terms of memory. And that's why this structure is much more efficient than the structure of the array, to where I had to allocate ahead of time the entire space and then get into the problem of either poor utilization or overflow. Okay, let's see now how we're gonna define the node. Well, basically, in the node, you're going to have as many entries in here as it takes. So usernames, IDs, passwords, student records, employee record, whatever. Basically, whatever data you use to put in the structure of the array. On top of that, you're going to have this extra pointer, which you're going to use later on to point to the next node in the linked list. And that's why the definition basically of the list as a whole of the node is something like the structure, list node, and then list entry. This is a predefined type, which basically could mean integer ID, character pointer name, grade, whatever. Okay, so bunch of entries in there. For simplicity and for shorten here, we're just talking about some sort of a predefined data type called list entry, and then the variable name is entry. Okay, so in here I will have my actual data that I'm gonna store. What's important and what's new in here is this one here. In here I'm defining next of type pointer of this type, the same as this. So inside the node, I'm defining actually a pointer of the same type as the node itself. So because actually, as I said, at the very end of every node, I should have a pointer that's gonna point to another node. So it's pointing to a node just like this one, and that's why we're defining it in here as struct list node pointer, calling it next. All right, so that's basically the one node definition, and basically it's something like this: data, and that's the entry here, whatever kind of data, and then a link that points to the next node, just in case it's going to be added to the list. And this is, of course, a pointer of the same type as the whole structure list node itself. All right. So that's the definition for the node. How about the list as a whole? Well, the list as a whole is defined fully by this pointer here, as a matter of fact. I just need a pointer of type pointer to node, and that's it. And just make it point to the first node in the list. Okay? So basically, my list could be just a pointer to a list node. And that's the whole thing. However, because I don't know how many nodes I'm going to have as I move on with the execution of my program, then it's a good idea to always keep a count, all right, an integer count of how many nodes I have. And for that, we're just going to make a very simple structure, which has basically two things inside it to define the what's so-called list. This structure is something like this. It's called list, and basically it contains an integer called count, and this basically is going to count the number of nodes in the list at any given time, and basically a pointer that points to a list node called head. And basically, I'm going to make this, once the list is initialized, to point to the first node in the list. So when I create the list, actually, I'm just creating a pointer called head, 4-byte pointer address in the memory, which is going to actually contain later on the address of the first node in the list once that list is created. Okay, so at the beginning, I just create the pointer, and that's it. Of course, I'm creating as well or allocating a space for this integer, which is going to count the number of nodes contained in the list at any given time. So basically, this is the structure defining the list. What kind of operations we can perform on the list now? Well, bunch of operations. I can create a no list node. Okay, and I can do this in the middle of my program because there is a new customer coming. So I have to accommodate him in a node. Okay. I can go in my list to a certain particular position. Go to the 10th node in your list, and in there, do so and so. So I can point to a particular node in a list. Insert a node to a list. I need to add physically a new node already created, filled with data, and I want to put it in the list. Well, and we're going to see we're going to insert that one. Or I'm done with one of the nodes and I want to delete it. Okay, we're going to see how to do that. Or, as usual, I could traverse my list, okay, visit every single node and do some processing on that node. Actually, we're going to implement all of these functions. However, in the remaining time of this lesson, we're just going to talk about creating a new node. So we can traverse it by finding the list size or by finding a target or doing whatever we would like to do. Let's talk about the first function, which is creating a new node. Well, to create a new node, what do I need to do? Step number one, I need to allocate storage for the new node. So I have, the space is not already allocated. It's not like the array. I don't have space for that. So the first thing you need to do is to create a space in the memory for the new node. Okay? And make some pointer points to it. Okay? In the memory. Step number two, initialize it. Fill the data you would like to add. Basically accommodate the new customer in his room. Okay? And then basically make, of course, it has a pointer to, that's going to point to next. Well, I don't have any next now. It's just one node. So usually, and it's a habit, make this always point to null. So 3 steps basically in creating the node. First of all, allocate space for the node. Then accommodate the data inside or put the data inside the node, and then make this node pointing to null. Very simple, straightforward. Let's develop the program for that, and we're going to end right there. It's called create node, and basically it's going to return back to me a pointer of type list node. So it's going to return to me this pointer, and this is enough to identify the entire block of the node. Okay, what does it take? It's only going to take the person, the customer, the data entry, the data you're going to insert inside the node. And I'm calling it X in here. Okay. The first thing I'm going to do, I need to allocate memory. So what I'm saying, I'm defining a local variable of type pointer to a list node. And I'm using the malloc function again. And I'm allocating, trying at least to allocate a space of this size, the size of the list node, this big of a space. Find a suitable place in the memory, okay? And please point to it with P. If successful, that is if P does not equal to null, okay, then I'm happy, memory has been allocated. So basically, initialize the node now. Put the data inside it, and make it point to null. So P arrow next is going to point to null this way. Otherwise, and that's when the P equals to null, that means no enough space in the memory to allocate for the new one, then we're just going to display an error message saying, well, sorry, I cannot accommodate this new customer. And that's it. Upon successful, I'm going to return this pointer P. So this is my return value. Okay? It's very simple and very clear. We're going to continue on this next time, but of course you can refer to this material in this lesson on the internet at the UNINETTUNO website. Click on the MidNet U and you're going to find all the material in there. Thank you very much, and I'll see you next time.